Just like Skank, Cavia, or the character video adapter, is designed in CUPL, this retro hardware design language from Atmel out of the early 80s. I'm using the same CPLD for it, the ATF1508AS in a package. It's basically an 84-pin PLCC package. It's a large CPLD with in-system programmability, also like Skank. So let's look at the inputs and outputs of Cavia. We have the Cavia clock as an input. This input is provided by Skank. It's basically 1/16 of the pixel clock, and it doesn't tick outside of the frame. It doesn't tick during the front porch, the back porch, or the sync pulse, either horizontally or vertically. It goes mute during those periods, because Cavia only knows how to read stuff from video and character memory and write stuff out to the Skank shift register. And it shouldn't do that when the monitor is not expecting data. It shouldn't fetch a character bitmap when the monitor is not expecting data. That's why the Cavia clock only ticks while the frame is being written, the screen itself, not the porches, not the sync pulses. Then this clock will stop and Cavia will just sit and wait. Now, this is the token code that Cavia will read from video memory. Once it addresses the video memory will spit out the code of the token that is stored in that address. Usually it's a number from 0 to 255. It's an 8-bit number, so the token code goes from bit 7 to bit 0. These pins are then used. And the outputs are the video address, which is basically the 11-bit address that's used to address the video memory, a 2 kilobyte video memory. And we also have the character address, which also has 11 bits, and it addresses the character memory as opposed to the video memory. The character memory is also 2 kilobytes. And then we have some buried states. We use the logic associated with these pins, but we don't make those intermediary results available to the outside world. They're only used internally. The main part are two counters: the token line counter, or TLC, here, this here. And it basically has 6 bits. It counts from 0 to 40. Why? Because that's the number of tokens in one token line. Remember, the screen is 40 times 30 characters. So each line in the screen will have 40 character tokens, identifying the respective character that should be printed in there. So we need to count that so we know when we are at the end of a line or in the beginning of a line. In addition to that, remember from episode 2, we need to pass over each line 16 times, 8 times for the different bytes of the respective characters, and then we have to print each byte twice to double the amount of information vertically and fill the screen. So we need to pass over each token line 16 times, and this is the counter. This 4 bits here, the line pass counter from 3 down to 0, these 4 bits will be used to count the current pass over a token line. And then finally here we have the fallback address, and the reason is once the system reaches the end of a token line, it will check whether it's the final pass or pass 16, or whether it has to go back to the beginning and do another pass. And if it has to do another pass, it needs to know where the beginning of the current line is. What is the first address? That first address will be stored by these 7 flip-flops here, the fallback address. And then you might ask, well, why are you using, well, actually 8. Why are you using 8 flip-flops if the video memory address has 11 bits? Well, the reason is that you don't need the 3 least significant bits because they're always 0. You see, the first address of a token line will be 0, 40, 80, 120, 160, always multiples of 40. And multiples of 40, the 3 least significant bits of that number in binary are always 0. So we don't need any logic to hold that state. We know in advance that they are always 0. Again, a little directive here to the chip to use its own internal pull-up and pull-down resistors, so I don't have to add anything outside. And here begins the logic. So the first is a token counter, a token line counter. So we need to know where we are in the line. Are we in address 0 or at the address 39 or the 39th or the 40th character of that line? For that, we use this counter here, 6 bits, and it's just like for skank. This is a 6-bit counter using 6 toggle flip-flops or T flip-flops, in which the input T of the flip-flop is the logical end of the outputs of the previous flip-flops. So it builds up the further you go into that chain. Now, the clock for them all is the Cavia clock, which is received from skank, but there is an asynchronous reset term. And what that term does is the following. When this counter tries to count beyond 39, from 0 to 39, in other words, try to address beyond the 40 tokens in a token line, it will reset itself. The moment it tries to count beyond the line, it resets itself back to 0, which is what it should do. The next one is the token line passes counter, or the line passes counter, LPC. This one has only 4 bits because it only needs to count to 16, actually from 0 to 15. And that's the maximum number of passes you need to do for every token line. It's not only the maximum, it's the minimum too. You have to pass over each token line 16 times. And then these 4 flip-flops will count that. The clock is again the Cavia clock, but now we have a clock enable term. So this clock here will only tick on the Cavia clock, and if the clock enable term is asserted. In other words, if it's true, positive, 1, whatever you want to call that. And when will it do that? If you check here this equation, the way to read this equation is the following. A clock enable will be true if TLC5 is 1 and TLC4 is 0 because there is an inverter, and TLC3 is 0 and TLC2 is 1 and TLC1 is 1 and TLC0 is 1. Now if you convert that from binary to decimal, you see that it's 39. In other words, the line passes counter will only count when the end of a line, the maximum address of a line, 39, is reached. In other words, when the token line counter reaches 39, then the line passes counter will increment by 1. You see the logic there? Now it gets slightly more complicated. It may look intimidating, but it's not. Bear with me. This is the video memory address. So this will be telling the video memory which drawer we want to open from it. Now, in principle, it's just a counter like you've seen before. There are 11 bits, video address 10, video address 9, video address 8. They are all toggle flip-flops or T flip-flops, as you see here. And if all there was this, if you ignored this stuff here, if you ignored all this stuff and only looked at this, you would see that this is just a counter. It's just an 11-bit counter like we've seen several times before. It's yet another counter. But this one has some extra logic, and it's based around this term here, LD, for load, which is defined here. And if you check the logic that you see here on the same way I've hinted before, TLC5 has to be 1, TLC4 has to be 0, TLC3 has to be 0, and so on and so forth. What you will see is the following. The load will be asserted, it will be true, it will be 1 when the final address of the token line is reached, but we need to scan it again. In other words, when the line passes counter is not yet 15, so we need to pass again, and when the token line counter address has reached the end of the line. So on that occasion, when the end of the line is reached, but we need to scan the line again, then this load will be asserted, and what this logic here means is that the fallback address, FBA, will be parallel loaded into the counter at that point. In other words, suppose you are at address 39, and you have to scan the first token line again, so you have to go back to 0. And if you are at address 79, which is the end of the second token line, but you have to scan the second token line again, then you go back to 40. So in the first case, the fallback address was 0. In the second case, the fallback address was 40. And this is the logic to make sure that the fallback address is loaded in that situation at the end of a token line when you need to do another pass. So it looks complicated, but it's in essence just what I told you. The terms get simpler as we get to the least significant bits, and these three equations here are slightly simpler yet. And the reason is, like I mentioned to you before, the fallback address is always a multiple of 40. It's 0, 40, 80, 120, and so forth. So the three least significant bits are always 0. And knowing that, we can just simplify this equation by hand, because we know that FBA2 is 0. So we don't need to put it in here. We just optimize this for the case that it's 0. And the same for VA1 and VA0. And the clock is the Cavia clock. Now we need a logic to store the fallback address, because the fallback address keeps changing depending on which token line you are in. If you're in the second token line, and the fallback address is 40. If you are in the third token line, the fallback address is 80. So how do we update the fallback address? Well, the fallback address is in principle just the video address, except that it will only latch the video address on this condition here. This is a clock enable. So this term will enable the clock, which means that the clock will only tick when this term is asserted, and the fallback address will only latch the video memory address on that clock tick, that enabled clock tick. So when does that happen? If you follow the logic here, it's using some states of the line passes counter and some states of the token line counter. If you follow what's happening here, they all have to be 0 for the clock enable to be asserted. And that means that this logic will only latch the video address into the fallback address on the very first address of the token line on the start of the first pass, which is exactly what we need. We need it to be able to go back to where it was in the beginning. So how do we know what it was in the beginning? Well, by latching that in the beginning. Essentially, that's the logic here. And the final thing, and this completes the design of Cavia, is we have to construct the character byte address that we will send to the character memory. Here we need to make a small intermission, because there is something I didn't tell you in part 2 for the sake of simplicity and brevity that we, however, need now, so you can follow along the next part. So bear with me a little. The character tokens, their respective code, are typically sequential. So for instance, the character corresponding to the letter O has a token code 52, that corresponding to the letter P has a token code 53. In the ZX81, you have token codes from 0 to 255, if I remember correctly, so we can capture them in 8 bits, and they are sequential, with a unit difference between subsequent token codes. The problem is that if you interpret these token codes here directly as addresses for the character memory, you will not have space in the character memory for anything but the first byte of each character map. So if this is an address, suppose it will point to a certain position here in character memory, and it will correspond to this contents of the character memory. In other words, a byte specifying the first line of the bitmap of character O. If 53 is interpreted the same way, then it will actually point to the second byte of character O instead of character P. You see? So your actual memory, video memory addresses, they are in a line like this, and each one of them, the contents of each one of them is a token. If you put the token code here, say 52, which is what you actually do, you put the token codes in the video memory. So suppose this would point here to this address in the character memory, corresponding to this first byte here of the character O. Now suppose you're writing the word oppression on the screen.
So the next token code will be 53, which is the one corresponding to the letter P in oppression. Now, if you again interpret this code as an address, it will point to the next address in the character memory. And then you will not have space for the other 7 bytes of the character O, because the immediate next address is already the first byte of character P. So this will not work. What we actually have to do is we have to take each token code that is here in the video memory, and the hardware has to multiply each one of them by 8 in order to create space for all the 8 bytes in each character map. So suppose you have the O, 52 times 8, suppose it would point here. Then the next one is 53 for P in the word oppression. And then you would also multiply this one by 8. The difference between them is 1, so times 8 it would be 8, and it would then point here. That would be the first byte of the bitmap of character P. And you would then have space for the other 7 characters in the bitmap, the other 7 bytes in the bitmap of character O. So this is what the hardware has to do. It has to take each token code, multiply by 8, and that will then be the character address in the character memory of the corresponding token. Now, the good news is that you actually don't need to have any multiplier hardware at all to do this. You do this just by wiring, because take this for instance. If you multiply 7 by 8, you get 56. Now look at the binary. 7 is 3 ones. If you multiply that by 8, what happens is the 3 ones in the original 7 are shifted to the left by 3 positions, these 3 positions here, and the space opened up is filled with zeros. You can generalize that for all multiplications for a power of 2. If you multiply a number by a power of 2, all you get is a shift to the left by that power of 2, say m. So in this case here, 8 is 2 to the power of 3, so you just shift 7 to the left by 3 positions, and you get this, which is indeed 56. So this is general for all multiplications by powers of 2, and so you don't need multiplier hardware, you just need to wire things in such a way that they are shifted to the left. And that's not the only advantage. Remember, if this token here points to this address in the character memory, in order to print on the screen not only the first byte, this first byte is the one here in this address there, but you have to print the other bytes as well. So in order not to print only the first byte, you have to add something to this offset in order to point, let me clean this up, you have to add something to this offset in order to point to the next byte, and then add something more in the next pass in order to index the next byte, and so on and so forth until the last byte. So you have to add from 0 to 7 in order to cover all the bytes of each character. So do you need a ripple carry adder circuit to do this? No, you don't need that either, because you see, if you shift everything to the left by 3 positions, then you know that the 3 least significant bits of the result are always 0. And 7 in binary is 1, 1, 1. And these will overlap exactly with the 3 zeros of the operand. So to add 7, or to add 0, 1, 2, 3, 4, 5, and 7 to this, all we need to do is to wire the bits corresponding to 7 to the 3 least significant positions of the original operand. You just append the bits of what you're adding to these 3 positions here, which you know are 0 because that's the result of a multiplication by 8. So the whole thing is taken care of merely by wiring.
So we will get 8 token code bits, TC7, TC6, TC4, we will get that as an output of the video memory. But as we discussed earlier, that's not enough, because each of these token codes will actually need to refer to 8 bytes, not only one. So what we do is the 8 most significant bits of the character address are just the token line bits. That's all there is to it. We just move token code 7 to character address 10, token code 6 to character address 9, all the way down to token code 0, which goes into character address 3. And then we are left with the 3 least significant bits of that address, which again are just the 3 most significant bits of the line passes counter. So just like we talked about earlier now. So it's as simple as that. We just wire these bits up to the right pins, and we get the functionality we need to have. Or do we? So that's what we have to go and test now with the logic analyzer.
So out goes Skank, which is already tested, and in comes Cavia to be tested. We will also need to change the wire harness so we capture the correct signals from the development board.
Alright, let's look at the data we've acquired with the logic analyzer. I will be looking first at the video memory address, the 11 bits generated by Cavia to address the video memory. This is the point T here where the acquisition started, and then you see the signals changing in time. You can go forward like this, and here below you have an overview, although in this case it's not very useful because it's highly compressed. I've acquired 32 kilobytes of data, so you get this compressed view, doesn't tell you much. And this tells you a lot, but it's probably easier to just go to a numeric view. And we even changed these hexadecimal numbers here. We changed those to decimal, so it's easier. So what we are seeing here in this column is the video memory address produced by Cavia. If this is working okay, the address will go all the way to 39 here, and then it will loop back to 0, and then again up to 39, and then loop back to 0, and that will repeat itself 16 times, and then it will count through to 40, to 79, and then it will go back to 40, to 79, go back to 40, 16 times, and so on and so forth. So let's see whether it's doing that. It's counting 1, and then 39, and it goes back to 0. The fallback address is 0, and it's parallel loaded into the counter, so it goes back to 0, and then it will count to 39 again over here, and then it goes back to 0 for the second time. So it should get to 39 16 times. This is the second. We can count whether this will be the case. This is the third. No, this is still the second in here, and this is the whatever. Let me count this from the beginning to make sure that this is working okay. Yeah, so this is the 16th time that address 39 is reached, and then it doesn't need to do another pass on that token line. It has done 16 passes already, then it counts through to 40, and then now it will go to 79 and then fall back to 40. Yeah, 79, and then it falls back to 40, and then this should happen again. 79, and it falls back to 40 right here, and then this should happen 16 times. And it's exactly what it does. So the 16th time it reaches 79, it counts through to 80 because it doesn't need to do another pass on that token line. It has done already the 16 passes, and now it will count to 119. Yeah, there it is, 119, and then it falls back to 80. So yeah, it's working just fine. I'm going to go through the entire list to make sure that there is nothing wrong, but now clearly the logic is working just right.
So now we change the wire harness again to capture a different bus, this time the character memory address bus.
Okay, this is the same thing, but now we are looking at the address for the character memory, not the video memory. We still have those 11 bits. These are just the logic analyzer probe identifiers, but basically these are the 11 bits of the character memory address. which is basically an indexed version of the address of the first byte of the character that we receive from video memory as an output of the video memory. But the video memory is not hooked up, so those inputs will default to 0. So all we will see here is the indexing, is that addition of 0, 1, 2, 3, 4, 5, 6, and 7 to that base address that in this case will always be 0. So what we should see in this case is that index going from 0 to 7 and then back to 0 and up to 7 and back to 0. And each pass should have should stay there for 80 clock ticks. I will explain why. Let me just change the view again so it's easier to see and explain. Okay, here we start. So this is the first index. So the first was actually 0, so this is already 1 because of the way I configured the trigger in the logic analyzer. It will always look for a 1 to start. So let's go through this cycle all the way to 7. It's counting correct. 4, 5, 6, 7, and then it goes back to 1. Yeah, it goes back to 0, I mean. Okay, so this is a clean start. So it has to be 0 for 80 clock cycles. Why? Because remember, each token line has 40 characters, and you need then to print the first byte of each of the 40 characters. So that goes from 0 to 39, or 40 instances. But you need to do that twice for each byte, because you're printing the same byte twice. So this index has to stay constant for 80 cycles. So let's see whether this is the case. This is 560, so it should end at 639, the 0. Oh, went too far. Yeah, 639, that's the last 0, and then 640, it's the 1, and that should go until 719, I think. Yeah, 719, here it is. Then it goes to 2. Yeah, no, this is working. 3, 4. Yeah, this is working. So all you are seeing are the least significant bits, which are these 3 here in probe A0, A1, and A2. The others, the other 8, are always 0, again, because we are not hooking this chip up to the video memory, so we don't get the base address or the address of the first byte of the character from the video memory. So this part I can't test, but it's so incredibly simple. We are just wiring the output of the video memory into these signals here, so not much can go wrong in there. The chance, well, everything is working according to my design intent. The chance of error now, I think, is limited to my design intent being wrong, and history knows that that chance is pretty high. It's not small at all, because you only know actually what each component needs to do once you start putting them together. So that will be the next step. I haven't done it yet the moment I'm recording this, so it's a mystery, but I feel encouraged by all these positive test results of the chips in isolation. Let us hope this has been the most difficult part of the project, except of course for modifying the firmware or the kernel code, which is always tricky, very lengthy, and not very pleasant. But hardware-wise, I hope the worst is behind us.